Yes, class. So in the last class, we had started with work, energy, and power, and we had seen what was the concept of work done. That is, it is the dot product of force and displacement. And if the force is variable, then we use the formula. Then we integrate it, f dx from x1 to x2. Then we were at the graphical method. We had seen that for calculation, what do? We calculate the area under the graph. If the shape is above the origin, we take it as positive. If it is below the axis, then we take it as negative. Then we had started with energy, kinetic energy, and potential energy make the total mechanical energy. So we had started with kinetic energy and we had derived the work energy theorem. Now we were at this change in momentum by percentage change in kinetic energy. So yesterday Zainab's answer was 22%. Yes, Zainab is present today. Huh. Other students, you didn't answer. Only Zainab, I remember, she had answered and her answer was 22%. Now see, percentage change in momentum. Okay, Zainab, your answer was 22%. Okay, percentage change in momentum is 10%. Percentage change in kinetic energy we have to get. Let's see whether it's correct or not. Okay, see, firstly, the change in momentum, the new momentum. It has changed 10% of the original, means this has increased by 10%. So this is 10 by 100 P plus P. So it is 110 P by 100. And then it is equal to 1.1 P. So what is the new kinetic energy? This is equal to P square, P new square, that is P dash square by 2m. That is 1.1 P whole square P whole square divided by 2m. See, mass of the system won't change because momentum has only changed. Now, see, this is 1.1 P by 2m. So when you are calculating the percentage change, how do you calculate the percentage change? It's the final kinetic energy, whatever is the change, that is initial final kinetic energy minus the initial kinetic energy divided by the initial, and then we multiplied by 100. So actual kinetic energy was P square by 2m. So once we take it, final is 1.1 P whole square by 2m minus P square by 2m divided by kinetic energy is P square by 2m into 100. So if we take P square by 2m common from here, we are left with, this is 1.21. 11 into 11, so 1.21 minus 1 divided by P square by 2m into 100. So P square by 2m, P square by 2m gets cancelled. This becomes 0.21 into 100. So this is equal to almost 21%. And one thing, see, this the change in percentage, change in momentum was 10%. So this is 21%. Roughly it is 2 times. Write it and then the next question you all will answer. Write it down. So it says a bullet weighing 10 gram is fired with velocity of 800 meter per second. After passing through a wall 1 meter thick, its velocity decreases to 100 meter per second. So it means initial velocity is 800 meter per second. Final velocity is 100 meter per second. Displacement is 1 meter. And mass is 10 gram. So 10 gram, firstly, you have to convert it into kg. So 10 to the power minus 3. So this is 10 to the power minus 2 kg. Now, first part says change in kinetic energy. What is the change in kinetic energy, class? Final kinetic energy minus initial kinetic energy. So half mv square minus half mu square. So this is half m you can take common. This will be v square minus u square. So you can put the values. Okay, Abir has got the answer. So this is half. Uh, 800, no? 800 square. 3150 joules, correct. Good. So this, yes, this you can solve. I'm stopping here. Change in kinetic energy. Work done by resistive force. See, displacement is given. You have you have to calculate the work done by the resistive force. If the bullet is moving, see, firstly, what will be the force? Mass is given into G. So mass is 10 grams. This is 10 grams into G. So this is 10 to the power minus 1. And displacement is 1 meters. So work done will be 10 to the power minus 1 joules. That is 0.1 joules. This calculation portion is enough. Calculation portion, see. This, I'm not calculating it right now. You can calculate it. This is 1 by 200 here. This is minus 64. This you have to solve. Answer will be negative, but kinetic energy can never be negative. And since it is a resistive force, that's why you'll get the answer in negative. So you subtract these two. See, this is 64 here, and you just have 1 and divide it by 2. So that's how you will get 3 by 2. And in the numerator, you have the 6 term. This, I think you all can solve now. Last portion says average resistive force of it. See, when you are calculating the average resistive force, firstly, you should know which things we have calculated and what all things are required. Like if you know you have the final velocity with you, correct? Then you'll have the initial velocity with you. So final velocity is present, initial velocity is present. So when you used it, you got the work done. Now see class, one more method is there for work done too, that you can directly escape it because the force is calculated here only, average resistance force. So you can make this as your third part answer because second part no need to make so many calculations. Let's make this as the third part's answer. Second part can directly be written. See, work done is equal to the change in kinetic energy. So whatever you will get in the first part will be the answer of the work done. So write it. Okay, class. Now the types of work done. So you have the positive work done. Positive work done means your cos theta will be positive. So for positive cos theta, you have to get the acute angle. Yes, Jobita, what is meant by acute angle?
Angle greater than 90.
Less than 90, 0 to 90 degree. Correct. That is acute angle. Then we have the next category that is between 90 to 180. That is obtuse angle, where we get cos theta negative, like cos 180 degrees minus 1. So this is negative work done. Then we have zero of the work done, where two things can happen. One is that either you get the angle as 90 degree, so you're getting the work done as 0 because cos 90 is 0. Or the next thing is possible is that either force or displacement, any of these is 0. So if it is 0, work done will be 0 because the quantity will be multiplied to a 0 quantity. Okay, write down the types of work done, then we'll discuss the conservative and non-conservative forces. So, Jesleen, Jobita, no, not Jobita, Jesleen and Zena, please revise conservative forces because I'll ask you things. Rest, Laika, Sabiha, Ali, Alina, Abir, write it down. See, always write the positive work done and everything, not just by the graph. You have to get it mathematically also. So it is based upon the angle. Yes, Jesleen, what do you mean by conservative forces? Jesleen. A force done in moving a particle from one point to another. A force done in moving a particle from one point to another. That is conservative force. Any force can be conservative force, it means. Incorrect answer. Conservative forces are those forces where the work done. See, you have to talk in terms of work done. Where the work done does not depend upon, yes, independent of the path. Correct. Like if this is point A, this is point B. There are many paths which I can follow. I can go from A to B like this. I can go from A to B like this. I can go from A to B like this. So we have here work done 1, here we have work done 2, here we have work done 3. All are independent. It just depends upon the initial and the final point. Means your total work done 1 is equal to work done 2 is equal to work done 3. It just depends upon the initial and the final point. This should be kept in mind. Okay, so forces in which work done is independent of the path. It depends on initial and final position. Now, gravitational force, electric force, elastic forces, these are all conservative forces which are present and which are conserved in your system. That's why we have the term conservative forces. They are conserved in your system. Now, look, we have studied the concept, all of us have studied the concept of these internal forces, external forces. So, you should know if a system is there. Suppose this is sun. And here you have Earth, which is present. Now, between Sun and Earth, there will be a gravitational force. This value of gravitational force will be calculating in the chapter Gravitation 2. So, if this is my system means the part under observation. So, according to this figure, my system will be Sun plus Earth. That is this entire sphere which is present, the entire orbit. This is the system. Anything which is left outside, there are other planets also. These are called as the surrounding. And total, we say system plus surrounding is equal to the entire universe. This is the concept of system and surrounding which you should be aware. Now, when we're talking about closed path, work done by conservative forces is 0. We call this as a cyclic force also. So basically, it's the work done by conservative forces is considered to be 0. And here only the concept of potential energy is valid. That's why we are studying this. In order to introduce the concept of potential energy, we are studying this entire. So potential energy is valid for conservative forces only. Then what are non-conservative forces? Just the opposite. Work done depends upon the path. If I have work done from first to final point like this, and then I have from initial point to final point like this, and then I have in a random arbitrary manner, then these are not equal to each other. All these work done are not equal to each other. And Best examples of conservative forces. Firstly, your frictional force. Friction force is a conservative force. Your viscous force. Viscous force you all don't know. We'll be doing it in bulk properties of matter. Write it till here, then I'll start with the concept of potential energy.
Ma'am, could you scroll up for 1 second? Then, ma'am.
Now, let's understand what is meant by potential energy. So, we have studied that kinetic energy comes into action when what? When there's a velocity produced. That is, the body goes into the state of motion from the state of rest. So, it's the energy possessed by a body due to the change in position, size, or configuration. So, you have gravitational potential energy, electrical potential energy, and lots of potential energies are there. But this concept is very old now. That change in position, change in size, and change in configuration. You all are in class 11th now, and this concept is valid till your class 10th only. Now, you have to understand things through a different perspective, that is the conservative interaction. So, what is meant by a conservative interaction? See, the term interaction, this means forces. So if two objects are are arranged in such a manner that they are able to exert forces on each other, we say they are able to interact with each other. Means they are nothing is coming in between them. So they are in the vicinity of each other. So they can be considered as conservative. It can be considered as a conservative interaction. Like two charges are present, plus q minus q are present. And let's say one more charge I have, plus 2q. So this can interact. So there can be one potential energy present. These two can interact. So I'll have one more potential energy. These two can interact. So I'll have three potential energies. Had there been one more charge with which could interact with other three, then we say there are potential energy. Now, this is a portion from your class 12th, actually, your charges. From your class 11th, let's say masses. Let's say this is small m mass, this is capital M. They are able to exert gravitational potential energy on each other. So there will be a potential energy. Now see, in this case, you have no change in the configuration, size, position, or anything. So it's actually the forces. If you see two objects are able to exert force on each other, they are able to interact with each other straight away, mark it as conservative interaction. That is, you will be having all these will be leading to potential energy in your system. Okay. And work done against the force, conservative force, it is stored in the form of potential energy. Okay. So work done, if it is non-conservative, then it will dissipate as heat, like viscous force and friction force. So friction force, all of you know. Viscous force is something new. Viscous means something which is thick. Thick, like you have seen honey. If you touch the honey, the texture of honey, that is called viscosity. That is viscous. So that resistance which you feel, if you put your finger into a glass of water, you will feel no resistance. But if you take a glass of honey and you put your finger into it, you will feel a resistance. So this is the difference. That thick or that resistance which is coming is called the viscosity. Now, concept of internal and external forces. See, if in your system, suppose this is your system. Any force is acting within the system. We say these forces are the internal force. And if any force comes outside the system, whatever is the magnitude of it, we say these are external forces. Okay, so internal forces are forces within the system. And one more concept, like one example which I had given earlier, suppose rocket is there, the exhaust is being ejected. So the force that is being applied within this rocket and exhaust system is the internal force. And suppose the force above and the force below cancel each other and the net force is zero. Then we say it is isolated system. Okay, write it till here, then we'll discuss work potential energy theorem. Write it till here first.
or configuration.